Hello and welcome back to chapter 23. For this video, as was promised in the last one, we're going to do a little bit of a departure in the way that we've been using Gauss's law. And so far we've been using Gauss's law to help us derive the electric field expression for a given system, knowing what the enclosed charge is. So we've basically been taking systems of charge where we already know what the electric field is, and then we've been reproducing those expressions using Gauss's law. But the only way that we've really been able to do that is that we already knew how the charge in the system was distributed. And not only that, the way that we've been using Gauss's law to define the electric field in any given system is in such a way that we've always had uniform field magnitude at all points on the surface of our container. And there are going to be some instances where we don't have uniform electric field. And if that's the case, it's going to make it difficult to try to find the appropriate container for these charges. So instead, we're going to try going the other way with the math, where if we already have a measurement of the electric field, can we go backwards in the math and find out how much charge we're dealing with. So for that, we're actually going to take a step back in the definition of Gauss's law. If you remember back in the first video, Gauss's law was defined as relating the enclosed charge to the electric flux in the system. And so it is the electric flux that we have been using to help us derive the electric field magnitude. But now we want to go the other way. We want to figure out what the charge is. So one way to do that is, if we already know what the electric field is, then we can plug that expression into our integral. We can carry out the integration to produce the electric flux, and then all that's left is to multiply that by the permittivity constant of epsilon naught. Now, easier said than done. First thing we have to do is we have to get that electric field expression. So to help us out with this, what we're going to do is we're going to set up an example problem where the electric field has already been established for us. So we're going to take an electric field of, and actually we'll produce this electric field in component form just so it's a bit easier for us to deal with it. We'll say 3 I hat plus 5y j hat minus 2k hat. And then the units will be in newtons per coulomb, as the units of electric field should be. Now you'll notice in this expression, of the 3 components that we have, 2 of them are constants, but this y component of the electric field has a variable of y as part of the term. And so this means as we move through space, specifically along the y-axis, the component of our electric field is going to change. Now, the only way that we can have an electric field change is through the influence of a charge. We know that electric charges produce fields, And so if we're going to see an electric field change, it has to be because of the influence of a charge in the system. Either we're getting closer to a charge or further away from a charge. And if that's the case, if the field is changing, we know that there's a charge there. Can we somehow capture that charge with a container, like a Gaussian surface, and then use that information to tell us how much charge is inside of that container? So here's what we're going to do. This is the electric field that we're going to work with. I can't really produce a magnitude for this electric field statement because one of the components is variable. I am going to draw a 3D reference frame, or at least attempt to do so. And it's probably not a bad idea to establish the proper notation of a 3D reference frame. There is a correct way to draw these reference frames, and this is actually going to become important for us in some future class discussions. And so what we have here is the traditional, what is known as the right-hand reference frame. And there, because we say that there's a right-hand reference frame, does that mean that there's a left-hand reference frame? And yes, there is, but to avoid any confusion, I'm just going to use this reference frame for the course material. I won't deviate from this, so everything that we do will be with respect to the right-hand reference frame. And then if you go on to any future coursework where your professors want to use a different reference frame, that's their prerogative, but I just want to keep any confusion to a minimum here. So now that we have our reference frame, we can move out to pretty much any location within 3D space, including the negative directions if we need to. But I'll just keep us in the positive region for right now. And I'm pretty much blind in terms of where these charges are going to be. You know, these charges are so small. The only thing that we've been able to do so far is measure what the electric field looks like. So at any point in 3D space, at any XYZ point, I could come up with a magnitude for what the electric field looks like. And so I want to see if I can capture some charge. And the way I will do that is I will make myself a container. And the container that I'm going to make is going to be a cube. And again, I'm going to try to draw this the best that I can. Let's see if I have to redraw it at any point. Trying to draw 3D on a 2D surface is not always the easiest. Okay, that actually doesn't look too bad. So that is our cube, and we'll say that each side leg of that cube is a value of A. So each side length of our cube is A, and as we can see on the reference frame, if we allow each of these to be centimeters, actually, let's make our life easier. We'll go with meters, so we don't have to introduce a bunch of extra decimals. Okay, so each of these will be meters, and so what we have here is a cube with side length 4 meters, and so a volume of a cubed. Stick that into your calculator. But so now that I have this container, we have an electric field with the 3 given components, and those electric fields will pass through the surface of this cube. Now, what makes this different from the previous examples that we've seen is that the amount of electric field that passes through any given face of the cube is not going to be the same as the other faces. And this is why the previous use of Gauss's law was so intent upon having a uniform electric field at all points on the surface. There's probably not going to be a very simple means of mapping out where the electric field is uniform throughout this system, and that's because it's constantly changing as we move. So we're not even going to try. But that's why we're looking for the charge. We already have the field. We already know what it is. It's right there. That's our function. But Gauss's law says if you can add up all of the electric fields that pass through the surface area of your container, then you have the flux. And once you have the electric flux, you then have your enclosed charge value. Well, we need to take this idea of flux as a closed surface integral, and we're going to back this up a little bit. Remember that the integration process is really just a means of addition. It's just a way of summing things up. And the dot product is a means of taking those two vectors and combining them into something that produces a scalar quantity. And scalar quantities can be added up no problem. We don't have to worry about directional components of the vectors. And so let's see if we can take this and turn it into a summation instead. There's really no reason we can't do that. And the reason I'd rather write it in this fashion is because I have 6 independent faces of this cube that I can treat with the dot product method, and then once I find the electric flux that passes through all 6 faces, I can just add them all up, because those dot products are going to produce scalars. So to get the net flux for this cube, I need to add up all of the individual flux values for the 6 faces of this cube. So with that in mind, we have see, we've got the front face, back face, left face, right face, top face, bottom face. Alright, so we have the front face, the back face, the left face, the right face, top face and bottom face. So we're going to go through and find out just how much electric flux is associated with each one of these faces. And we're going to do that by using our definition of flux. So for the front face, we'll start with the front face. And the front face is right. I'll use a different highlighter. So the front face is right here. So we're out here at an X value of 4 centimeters. So that's where the front face is. And as far as the electric field goes, we have the components of the electric field, but I need to compare that electric field vector with the surface area vector of the front face. Well, that front face, which way is it facing? Well, hence the name, it's facing towards the front. In other words, we have an area vector for the front face, which is pointing in the positive x direction. So dA is pointing in the positive x direction. And we need to take the dot product of that with our electric field vector, which has 3 different components. We have an x, a y, and a z component. Now, when it comes to the dot product, we can carry this multiplication through, and so each term within the electric field expression will have a dot product with the area vector. So we have 3 I hat dot dA I hat, which actually we don't even need dA anymore because we know what the dimensions of each face of the cube are. We can say right now that every face of this cube has an area of 16 square meters. So we can even simplify this even further. So we have 3 I hat versus a 16 I hat, and whenever we evaluate a dot product, it is the magnitude of each times the cosine of the angle between them. Now keep in mind we're looking at each individual component of the electric field. So what we really have in this first step is Ex dot A, which are both in the I hat direction, which means that the cosine theta, the angle between 2 components that are pointing in the same direction, is 0. Cosine of 0 is 1. So we have 3 times 16 times cosine of 0 is 1. 3 times 16 is, I believe that's 48. And so there's the dot product of the x component of our electric field with our surface area. But then we need to go through and do the same thing with the y component and the z component. But when you attempt to take a dot product of 2 vectors that are in different axes, the I hat and j hat, those are representing x and y directions. Those are 90 degrees with respect to each other. And so if we attempt any kind of dot product with these, we're going to get a cosine 90, which results in 0. Likewise with the k hat and I hat, we're going to get a 90 degree relationship, which is 0. And so out of this entire dot product of the electric field as it passes through the front face, The only thing that we get out of that is the contribution of the like terms. And if we think about that a little harder, when it comes to the electric field, that electric field has components that are pointing in the x, y, and z directions. And it is only that x component of the electric field that is actually going to pass through the front face of that cube. And so we can actually save ourselves a whole lot of work by keeping in mind that only the component of field that actually passes through any given face is actually going to contribute to the electric flux. And so now that we know that, let's take that idea and run with it. We know that for the front face of this cube, only the x component of electric field is actually going to pass through that front face because the front face is pointing in the x direction. And we know now that the flux for the front face comes out to be 48. Well, now we need some units. We can get those units right from the units of our flux expression. We have newtons per coulomb for field, and we have meters squared for the area. So there we have it. All of these flux terms will have units of newtons per coulomb meters squared. We just need to get the values so that we can add them all up. All right, well, now we need the back face. The back face of the cube is pointing towards the back. So the back face of the cube is back here. And it is facing towards the back. So we have a, I keep wanting to write it as dA, it's just A now. So we have an area vector that is pointing in the negative I hat direction. Again, the only thing that is going to pass through the back face is a vector component of the electric field that is pointing along the x-axis. And so that is, again, the x component of the electric field. So we have our x component of the electric field dotted with the area vector of the back face. The x component of the electric field points in the positive I hat direction, but the back face is pointing in the negative I hat direction. If we evaluate this particular dot product, we still get the magnitudes of the vectors along with the cosine of the angle, but the angle between these two vectors is no longer 0, it's 180 degrees. And the cosine of 180 is no longer 1, it's negative 1. We still have 16 for the area vector, and we still have the 3 for the magnitude of the x component of our electric field, and so this is resulting in a negative 48. Okay, so the front and the back face appear to be negating each other in terms of the electric flux. And that should make sense because this electric field vector that we have here with all of these components We don't really know how it's being generated. We just know that there are charges somewhere within the general vicinity that are generating these electric field components, but the X component of our electric field is uniform, which means as it points in the positive X direction, it basically just enters through the backside of the cube and then emerges through the front side of the cube completely unchanged. In other words, what comes into the cube just goes right back out in terms of the X direction. And so we get a net flux of 0 because of that. And this is an important concept because if having a uniform component of electric field along the X direction means that we get a net flux of 0 along the X direction, what's going to happen if I have uniform field components in another direction, like right here with the Z component? Well, I have a Z component that is uniform. This particular component is negative, which means it's going to be pointing in the negative Z direction. So it would enter through the top face and exit through the bottom face completely unchanged. And so again, we have a case where what enters the container exits the container, and we get a net flux of 0. We can go through all of the math to show that. We can come through here and we can set up the appropriate dot products for the Z component of electric field, which is pointing in the negative k hat direction, and if we start with the top face has an area vector that is pointing up in the k hat direction. And so what we would end up with for that top face, we would have magnitude of Z component, magnitude of area vector, and cosine of the angle that exists between the two. Well, these two have positive negative, which is going to result in an angle of 180. So that's another -1. The magnitude of the area is 16. The magnitude of the Z component is 2 magnitude. And so here we get a -32 Newton Coulomb meter squared. So that's for the top face. So we can come down here to the top face, -32. But then if we drop down to the bottom face is going to face down in the negative direction. And so all that this is going to accomplish is that it's going to switch the cosine 180 to a cosine 0, which will produce a +1. And that's going to produce a +32 Newton Coulomb meter squared. And so we get another 0. So it doesn't look like we're really accomplishing anything, but that's because our X and Z components were uniform. They were unchanging as they traveled through space, and if a field is unchanging, then that means that there's nothing there to change it. But now we need to to work on what's happening along the y direction. And this is where we will see things change, because we do have a changing field and magnitude along the y direction. And I'll clean up some of this so that we have some room to evaluate the dot product of our y component of field along with the left and right faces of our cube. So let's look at the left face of the cube. So for that left face, we need to take the electric field component in the y direction, which has a positive j-hat direction. We need to take the dot product of that with the left face, and the left face faces to the left, which is the negative j-hat direction. We evaluate our dot product by taking the magnitude of each vector and the cosine of the angle between them. Well, our angle relationship is 180. Cosine 180 makes for a -1. The area of each face is still 16. And, well, the magnitude of our electric field, how do we get the magnitude of a variable? And the answer is we can't. And so we will actually have to evaluate the electric field at the left face. And at the left face, everything about the left face here is sitting at a y value of 0. Because technically that back corner of the left face is touching the origin, where we have a y value of 0. So if I plug in 0, well, this is all gone, and I get a flux through the left face that is equal to 0. So looks like we still got a net flux of 0 going for us. So the only hope that we have left for getting any flux through this cube is going to be through the right face. And so we take our y component, which is pointing in the positive j-hat direction. We take the dot product of that as it passes through the right face of the cube. So here's the right face of the cube, and it is pointing to the right, which is the positive j-hat direction. We evaluate our dot product with the magnitude of each vector, the cosine of the angle between them. These are both pointing along the positive y direction, so we have cosine 0, which evaluates to positive 1. We have 16 for the area. And then, just like before, we're going to have to take the y component of our electric field vector and evaluate it at the position of our right face. Now, the right face is situated at a location where the value of y is equal to 4. Remember, each side of the cube was length of 4, so now the right face is sitting at a value of y equals 4. If we plug that in, 5 times 4 makes 20, times 16 times 1. And what is that going to be? I want to say like 360. I don't know if I'm doing the arithmetic in my head or not. I'll just grab my calculator quick. 20 times 16. I'm sorry. Did I say 360? I meant 320. Okay, 320 newtons per coulomb meters squared. So 320 newtons per coulomb meters squared. And, well, as nice as it might have been to have the net flux equal 0, turns out it's not. I actually get a finite value of 320 newtons per coulomb meters squared. And now we can use that back up here to evaluate how much charge is present inside the confines of our cube. Now, if we had had a net flux of 0, yeah, that would have made our world super easy, because if we have a net flux that is equal to 0, then that would mean that there was just no enclosed charge inside of the cube. But that's not what happened. We have a net flux of 320. We need to multiply that by the permittivity value, epsilon naught, and we will get the charge that was enclosed by our cube. Our epsilon naught value, that is 8.85 10 to the negative 12 times 320. Calculator time, 320 times 8.85 times 10 to the negative 12. And I'm getting 2.832 10 to the minus 9. And units of charge is going to be coulombs. And so there we have it. We have approximately 2.8 nanocoulombs of charge contained within this cube. Now, the one thing that this answer does not tell us is where that charge is inside the cube. All we know for sure is that we have that amount of charge inside the cube, and that's it. But that's the only thing that we can really say at this point. But now, if you notice, the value of the charge that we got here came out to be a positive. And so that tells us a little something about what kind of charge we have to have inside this cube. Because it's positive, that means we have to have a net positive charge inside of this cube. And if this net positive charge were made up of, let's say, protons, then how many protons are inside of that cube? Now that we know how much charge is in there, if those charges are made up of protons, then how many protons do we have bouncing around inside of that cube? And the way that we can do that is we can take the enclosed charge that we have and we can divide that by the value of the charge of a proton, which is equal to positive 1 elementary charges. And if you remember, the elementary charge was 1.602 10 to the minus 19. The enclosed charge that we have is in coulombs. The elementary charge has units of coulombs, so we're getting a unitless value here, but that's okay because we're just we're asking for a count. We want to know how many. So we're going to take our enclosed charge value. We'll divide that by the 1.602 and the 10 to the minus 19 results in approximately 1.77 times 10 to the 10 protons. So about what would that be? About 17 billion protons bouncing around inside of that cube. And granted, it is a pretty big cube. You know, this was 4 meters by 4 meters by 4 meters. But really, I mean, we could have made the dimensions whatever we wanted. Now, does this mean that there are no electrons inside of the cube? So that could be a concept check for one of our quizzes or our tests. But because I have that much positive charge inside of the cube, does that mean that there are no electrons anywhere? And the answer to that question should be no, not necessarily. All we know for sure is that the net charge inside of that cube is the positive 2.83 10 to the minus 9. So all this means is that we have an excess amount of charge equal to this. We could very well have an extra 10 billion electrons in there, along with an extra 10 billion protons, along with the 17 billion protons that is making up this count. So I could very well have 18 billion protons and 17 billion electrons. Sorry, let's do 1 billion electrons. So there could very well be some electrons inside of that cube, but electrons and protons have equal and opposite charges, and so at the end of everything, it's those excess protons that are giving us the enclosed charge value that is contributing to the electric flux. So that's not to say that there are no negative charges that exist inside the construct. It's just that they're currently paired with an equal and opposite amount of positive charge. All right. Well, now let's try another approach to this this use of Gauss's law. Let's say that you are sitting in your classroom. You're in your chair, sitting at your desk, waiting for your professor to come in. And your professor walks into the door carrying a box that has some charge in it. And so as your professor enters the room with this box of charge, there's a box of charge here, you find out that the electric flux for your classroom now has a value of, let's see what a realistic value might be. We'll say 500 newtons per coulomb meters squared. All right, so that is now the electric flux of the room once your professor enters the room with that charge. So, two questions. First question, what is the electric flux? Getting too close to the edge of the screen. The stylus doesn't want to pick up when I'm writing. So, what is the electric flux of the room before the professor enters with the box? And we're only considering the charge that is in the box. And then part 2, how much charge is in the box? So those are the two questions. So this is the electric flux after the charge is brought into the room, but before the charge is brought into the room, what would the flux be? And so if we take Gauss's law, there's Gauss's law in its simplest form, and then if we expand it into the most generic form of evaluating the electric flux, we get that. And I see students almost exclusively flock towards that second equation because they know that they're in a classroom. That classroom has, ceiling, wall, floor with dimensions and area that electric fields from the charge can pass through. And I agree. This charge, let's say it's positive charge. That charge is going to send electric field lines out in all directions. And so there will be a net flux associated with the room, and that net flux is right there. Well, I get so many people that focus on this part of the problem that they completely forget about the fact that they already know what it is. It's 500. And so we have a net flux of 500 Newton coulombs per meter squared, and you don't need to know the dimensions of the room. This flux has already been measured. All you need to know is what is the permittivity value, and we'll just go ahead and keep using epsilon naught until we have a reason to change. And that can go into our calculator. We have our 8.85 10 to the minus 12 times 500. And that's going to give us, let's see, uh, 4.425 times 10 to the minus 9 coulombs. Okay, so there it is. That is the amount of charge that was in the box that your professor carried into the room, and it didn't require any fancy math because we were already given the flux measurement. So what was the electric flux before your professor entered the room? Well, so now we need to take that box of charge back outside of the room and now consider the electric field lines that charge is producing. And what do you notice about the field lines as they interact with the room? And what you should notice is that as a field line enters the room, there is a flux associated with the entry, but then, well, that electric field line continues and it exits the room. And so any electric field that enters the room eventually exits the room. In other words, what comes in eventually goes out, and so we end up with a net flux inside of the room that is equal to 0. Well, why is that such a different outcome compared to when we had the box of charge inside of the room? So we'll bring that box of charge back inside the room here. Well, now you'll notice that there's only one way for the electric field to interact with the room, and that is to exit. There's no way for the field lines to enter the room from the exterior. All they can do is exit. And so every time we get an interaction with the field and the surface area of our container, aka the room, we only ever see the field lines pass out. We never see any of the field lines actually enter the room. And so that's the reason for the two answers. Another way that we could answer this question right here is just using the basic concepts of Gauss's law. If you're using your classroom as a Gaussian container, well, how much of the charge is currently being contained by the room? And if that charge is currently outside the room, well, there's no charge inside the room, so your room is not containing any charge, which means that the net flux for the room has to be 0, at least until your professor enters the room with that box of charge. One last little concept question. So let's say your professor leaves and brings back a different box, but this time when your professor enters the room with that box of charge, the net flux for the room is now a negative 500. So what does this mean? What has changed? Well, you have a measure of your electric flux, and so there's really no point in trying to mess around with this equation, because you already have the measure of the electric flux. So we'll go ahead and put that into the equation, which we've already got everything set up over here. So let's just sneak in a minus sign there for a negative flux, and well, that's going to carry through the math, and that's going to make the charge negative. So what's happened is that the first time your professor came into the room, your professor carried in a box that was filled with positive charges because we had a positive net flux associated with the room. But now your professor has gone back, emptied the box, and filled that box with a negative amount of charge, which was the reason why we now see a net negative flux associated with the room. So that charge value now has to be negative. Alright, I think that is enough for this particular video. When we come back, I think I'll do one more video for the chapter 23 material. It might be a shorter video. I think there's one more case scenario for solving for electric field magnitude, and that would be for the charged disk. And if you remember, for the charged disk, we were able to extend that disk out to infinity. In other words, we were able to turn it into an infinitely charged sheet. And so we want to see if maybe Gauss's law can help us in figuring out what that electric field should look like. So that's what we'll do for the next video, and then that will be it for chapter 23. And we'll move on to chapter 24 when we're done with that. So probably a shorter video this next time around.